What we are talking about is waves. Waves are the translation of energy due to the vibration of a medium in simple harmonic motion, as you see on the board over there, right? There's a couple key words in there. Simple harmonic motion, right, which is defined, also known as periodic motion.
When the vibration repeats itself over the same path for an extended time.
All right. Good. So repetitive vibrations. So ocean waves is a great example, right? And we're going to talk about a number of other ones here as well, right? The idea being,
I was just thinking sound.
yeah,
Like
sound is a great example. Good.
Is that?
Echoes is an example. Good. What else?
Like echo. A lot of things.
She's talking about echolocation. We're going to get to that. You're getting ahead. You're getting ahead. But for now, what we're talking about, basically, right, is energy moving over long distances, right? So to go back to the original definition earlier, the waves are the translation of energy due to vibration of a medium, right? First of all, vibration should be relatively easy to understand, right? Vibration is a repetitive motion in the same path over and over and over again, right? This is very common for a number of things that you can think of, right? The clock goes around in circles, right? That is a periodic motion. That is a vibration in a technical sense, right? Because it is repeating the same pattern over and over and over again. Some more familiar ones, right, are these examples that I have set up here, right? This one particularly is quite important. It's just a spring. I disagree.
With a weight energy. Oh wait.
A spring and a mass, yes?
Yeah.
And so what you see is the mass and the spring vibrating up and down in a vertical way.
Ew, we did this.
Oh, what about like
repetitive pattern.
instrument?
Instrument.
Like if you pluck a guitar string.
Strings instruments, yes. When you pluck a stringed instrument, the string vibrates back and forth, much like this, right? Like this giant spring that you see right here.
We did this
Is that okay?
Yes, and we're going to talk about that in just a second, right? Before we get to
If I
that.
brought in my ukulele, could you explain it to us how that works?
Yes. So the point, of course, is that these things repeat for an indefinite period of time, right? What we're going to be looking at is systems that essentially would be considered ideal. In other words, this should vibrate up and down, back and forth, to the same position at the top and the bottom, consistently forever, right? In the real world, that doesn't actually happen. We know that eventually that system right there is going to stop bouncing up and down, right? But the time frame for that is a rather long time frame. And so for all intents and purposes for this course, we are going to assume that that is going to vibrate the exact same forever, right? That is actually technically not true, and we can talk about why in just a minute, but for now, that's the goal, right? So there are three main vibrations that we need to focus on, right? One is an inline vibration, right? This is an inline vibration. In other words, the force that is making this move, right, is the force due to the spring. And so it is pulling up, and gravity is pulling down, right? And so the force that is making it vibrate is in the same direction as the actual energy of the system, right? In other words, the actual system is moving up and down, the forces are up and down, right? Well, I don't know if you need to write that down. You can if you want, but I mean, I'm talking, you're learning, right? So that's the first type of vibration. The second type would be a perpendicular vibration, right? That's an example of a pendulum. This is a pendulum, right? Hung from the ceiling. It vibrates back and forth, right? What force makes the pendulum move? Gravity. Gravity is what makes it move. Why doesn't it just fall on the ground? What force is preventing that happening?
String.
The string. What do we call that force?
Tension.
Tension. Very good.
Nice.
We call that tension. Tension is up. Gravity is down. This thing is vibrating left and right. So this vibration is perpendicular to the forces that are actually causing the energy to occur, right? So the energy being displayed is back and forth, even though the forces are up and down. Whereas here, the energy being displayed is up and down, and the forces are up and down. Make sense? Two very different vibrations. The third one is spinning in a circle, which is a little bit more complicated because that's a perpendicular for an entirely different reason. We're going to explore that after this unit. Right? Circular motion will be something we talk about separately. No, this is for other stuff I'm going to show you in just a second, right? There are a few terms that you need to know in order to describe this stuff effectively, right? The first of all is called displacement. Displacement uses the variable x measuring a distance from the starting point, which is the definition of displacement, the distance from the starting point.
So,
Distance from the starting point. In waves, the starting point has a very specific name, right? If I were to stop this, and I were to stop this, then we know that the force of tension versus the force of gravity, force of tension of the spring versus the force of gravity are balanced. They are equal and opposite. What do we call that state in forces when the forces cancel out to get a net acceleration of 0? Very good. It's called equilibrium. So the starting position is also called the equilibrium position. And that's an important term to recognize. At the equilibrium position, right, the forces are balanced and the acceleration is 0. Equilibrium. E-Q-U-I-L-I-B-R-I-U-M. Equilibrium position.
So what is that,
At the equilibrium position, the forces are balanced, which means that the net force is 0 and the acceleration is 0 because the net force is 0. Well, so this is an interesting characteristic because at the equilibrium position, what do you notice about these systems? They're not moving, right? So a vibrational system does not vibrate if it's at equilibrium, right? So if it has no motion, then it does not move. And this should make sense because the forces are balanced and the acceleration is 0. And the acceleration is a change in motion. Is all of this coming back to you, right? We're bringing in a bunch of things from first semester. It's at the equilibrium position when the forces are balanced. And if it starts at the equilibrium position, as you see with all of these items, then they do not move, right? Which means that they do not begin to vibrate until you add energy. And that should make sense because waves are the translation of energy. So if there is not energy in the system, then they are not vibrating, right? Where does the energy of these systems come from?
You.
From me, right? There has to be an outside force that overcomes the net force in order to change the acceleration, right? That was Newton's laws. Remember? All right. So each one of these systems does not vibrate until I add energy to it, right? Once I add energy to it, then we see the translation of energy due to the vibration. Now, translation of energy is the tricky term here, right? Translation is very similar to transformation. You remember the law of conservation of energy. Energy cannot be created or destroyed. It can only be transformed through work. So what we see in these systems is a translation or a transformation of energy. Translation instead of transformation because we're talking about not just the energy being displayed, but the energy itself moving from one place to another. So a little bit different than transformation because when we think about transformation, we were just talking about changing from potential to kinetic and kinetic to potential and vice versa. And these do that, right? If we stick to just the pendulum, right? At the ends, what kind of energy does it have? At the end,
Oh, wait.
it has potential because at the very end it stops for just a moment. At the middle, also known as the equilibrium position, now that I have added energy, what kind of energy does it have in the middle? Kinetic, because it's moving, right? And so what we see is we see a transformation from potential to kinetic to potential to kinetic, potential, and so on. But we also see a movement across from one position to another, right? And so the energy is over there, and now it's over here, and then it's in the middle, and so on, right?
So when it's in the
So
middle.
it's not just transforming, it's also moving. That make sense?
Translation of energy is when energy moves.
Moves and possibly transforms.
Wait, hold on.
When it's in the middle, it's kinetic.
Right, because in the middle, right, remember that the middle is the equilibrium position, and that means the acceleration is 0. So the system should not move at the equilibrium position, but if I add energy to it, then when it gets to the equilibrium position, it is already moving. And so its momentum causes the kinetic energy to be maintained until it transitions or translates or transforms into potential and vice versa.
I'm just, didn't like when we did like the problem on the slide, didn't it have like potential and kinetic and potential?
Exactly, and so there was actually translation happening there as well. We just didn't openly address it. Right, very good. All right, so same thing here, right? At the equilibrium position, it has no energy, right? Note that the equilibrium position is right here, right? Let me see, I brought out a Post-it so I can mark my spots. Right, let's see if I put this on the string, right where this is, right? The equilibrium position is right at the top of the Post-it, right? So if I extend this below or above that position, then I have stored energy into the system so that when I let go, it then translates that energy, right? It happens either direction, and what I end up seeing is I see kinetic energy at the equilibrium position, right where the flag is, and potential energy at either end, right?
Doesn't it have that energy?
Yes, it does.
Wait,
Elastic
hold on.
potential. Very
Why
good.
is that the equilibrium position if you didn't start there?
Yes.
It is when it's.
Wait, doesn't it have kinetic energy all
No, that was a great question.
Oh,
I can't start at the equilibrium position because at the equilibrium position the forces are balanced. So a starting position has to be where I add energy to it. So I can either add by adding potential and lifting it up, or I can add by adding elastic potential by pulling it down, right? My starting position and my equilibrium position in most cases are going to be a little bit different, which is kind of interesting to think about, right? However, it's not unusual for something like a guitar string, right? We argue that actually we start at the equilibrium position and then we add energy and then that's what causes it to vibrate, which is why it's fine to describe the equilibrium position as a starting position. Another way to think about it would be, instead of pulling on that, I could hit it with a hammer. And so that way it is moving immediately instead of having to pull it down and let go. Make sense?
yeah.
All right. Go ahead.
Dang it, I'll think of it.
Okay. So displacement is how far it moves from the equilibrium position, right? In the pendulum or the thing, right, that would be a measurement from the original position where it wasn't moving out to wherever it goes. Amplitude is the maximum displacement. And so instead of thinking about the entire range over which this swings out, we're talking about just the endpoints, right?
So would that be where you, like if you pull that down and then you stop, where you stop is at your amplitude?
Exactly,
Wait, so
right? So if I think about this as being the equilibrium position, there is displacement occurring as I move it, but the maximum displacement is right here when I let go, right? What's interesting about all of these systems is that the amplitude, and therefore the displacement as well, is symmetrical, right? And so whatever vibration is happening, if it, for example, this pendulum, however far it moves to my left, is also how far it moves to the right from the equilibrium position.
Wait,
So how would you
Right.
define amplitude?
Amplitude is the maximum displacement, and it can be both positive and negative. Displacement is going to be the range anywhere along here, right? If this is the equilibrium position, right? Displacement here, displacement here, displacement here is all a measurable value. But the maximum is the end points.
Oh, so
So x is how far it moves from the middle, whereas a is just the farthest point. A cycle is a synonym to vibration, right?
So just a
Specifically, one complete vibration is what a cycle is. Now, what do I mean by complete vibration? I mean,
Go back, go forth, and back.
exactly, all the way out, all the way back to the starting position, a complete cycle. So it has to be the same conditions. So if we think about it in terms of the pendulum, we have to return to the exact same conditions. So it not only needs to be out to my left, but it also needs to be on its way back, right? It needs to be on its way back because that's how it started, swinging that way. So when I count one cycle, right, I would count all the way out, 1, all the way out, 2, and so on, right? Just like you did in the pendulum lab. The same thing is true here, right? If I count a cycle, then I'm counting all the way up, all the way back to the bottom. All the way up, all the way back to the bottom, right? So in this case, it would be 1, 2, 3, 4, and so on. So depending on where I start, if I define this as the starting point, then it has to swing all the way out and back to where I started. If I define this as a starting point and I push it, then it would be to there.
Okay.
That make sense?
It's like
So it's not like-
back to the.
Back to the place that you started, moving in the same way.
Is it the equilibrium position you have to get back to that?
It depends on where you start.
But so
If I start at the amplitude, then a cycle can be counted from there back to the amplitude. But if I start at the equilibrium position and give it a push, right, then it's back 1, right? So if I'm counting from the equilibrium position, I start there, and then I count 1, 2,
Okay.
and so on. Make sense? Okay. So that's a key thing because cycles are what we're thinking of when we're describing waves, right? Waves, the vibration, is a repetitive pattern. And so what we're seeing is a cycle being repeated over and over and over and over and over again, right? In all of these systems, we're going to go ahead and just say that the cycle is ideal, that the amplitude on either side is symmetrical, and it will always do that, right? The reality is that because of friction and internal heat, right, the friction for this, up here at the top where the rope is attached to the metal, in the spring, actual heating of the metal as it bends and deforms takes away some of the energy in terms of friction. That's a reality that does actually happen, but for most purposes, if we were to time this only for 30 seconds, it's close enough to being perfect that we can just say that it is. That make sense? We don't have to get quite so complicated. Next thing, period, right? Capital T is a very specific time. It is the time for one cycle, right? Because these things are repetitive, we can't describe the time as being infinite. That wouldn't be useful, right? So we're going to be calculating things based on the time for one vibration or the time for one cycle. So we're going to be doing that. You did that in the pendulum lab by timing 20 cycles and then dividing by 20. Oftentimes you can just measure it directly. It depends on how fast it is. So that's period. And then of course is frequency, right? Frequency is specifically the inverse of period, right? What does that mean to you, the inverse of period? If period is the time for one cycle, then what is the inverse?
How often?
Very good. That's exactly right. How often it vibrates in 1 second, right? So we're going to specifically use the value of time as 1 second, and we're going to say frequency is the number of cycles in 1 second. This is really useful because that's often how we describe things, is based on frequency, right? We count how many times it vibrates in a period of time. The example that I used was a CD-ROM. CD-ROMs often spin so ridiculously fast that they're given as RPMs, which is something that you're fairly familiar with. What is RPM? Rotations per minute, right? So if we think about rotations as revolutions or vibrations, then RPMs is the certain number of cycles in a minute as opposed to a second, right? And that partly is because it's just easier in terms of
Is that in your car?
describing. Yes, RPMs would be what part of your car? What rotates per minute?
Wheels?
The wheels, and also parts function in the engine actually rotate in order to drive your car. So your car is measuring rotations per minute. Good, okay, so frequency and period are inverses. In fact, there's a formula for that, which is really simple. T equals 1 over F, which is the same as F equals 1 over T, because they are inverses, can be written either way. Okay, so each one of those systems is a vibrating system that repeats over an extended period of time for a similar path, right? The point, of course, is that these are just one object in the medium, right? So we're just looking at the mass swinging back and forth, or we're just looking at the mass bouncing up and down. But a wave, like in the ocean, right, is actually many, 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 many particles vibrating in simple harmonic motion, right? The actual water is going up and down, right? But what happens to the waves? They crash on the beach, which means that the wave, the energy moves from one end to the other, even though the vibration happens up and down, right? And that's exactly what this spring is for, right? If I take this spring, and I hold it here at the end, and I lift it up in the air, and then I let go, what do you see? You see a wave. That's exactly right. Right?
That's like if you do a what's that workout? The ropes?
Yes.
We keep it like a solid.
Just like that.
You do that again.
Yes. Now here's the point. If I think about, my post, oh, it fell down. If I think about any one particular part of this spring, it is only going up and down. Right? It is vibrating in simple harmonic motion up and down. And you can see that here once if I just go like this, right? The spring is going up and down. If I mark it just so that you can see it, right? The post-it goes up and down. What it doesn't do is go that way, right? Or this way.
Push it that way.
Right, but if I go like this,
Then it will move.
and I lift this up, the post-it does not move, right? The post-it vibrates.
What? The post does not move.
The post-it does not move left to right, right?
I
This
thought
is
you meant
very
move.
important for you to recognize. The ocean waves are vibrating up and down.
Whoa.
The energy is moving into the beach.
So it's just
This is
going-
very important because if the ocean was actually moving onto the beach, there would be no land, right? If the ocean was moving onto the beach, there would be no land because all the ocean would be on the land, right?
But
the ocean is vibrating up and down while the energy of that vibration is moving horizontally.
What happened? But if it was going left and right, like why are there waves in the ocean?
In the
All right,
middle of
so
the ocean.
let's talk about this.
That's like really stupid.
No,
If this thing is not moving, it's at equilibrium position. What has to happen in order for waves to exist in it?
energy.
We need to add energy. What is the only thing touching the ocean that could add energy?
Air.
Wind.
Air, wind.
That's why when it's windy.
How do they roll though? How do they?
The air blowing across the water causes a change in pressure which pushes the water around.
So if it
And then the vibrations of a bunch of water acting together, right, all combining together gives you occasionally useful waves that work
So
out.
what
Most of the
about-
time it just looks irregular like this, right? But if the vibrations work out just right, then you can get very interesting patterns. Right?
You can get like how you.
And
get-
that's exactly what we're going to look at.
How
Is
you
very
get-
interesting patterns. The point, of course, is that you're familiar with this because if you jump rope, right, swinging this around in a circle is a vibrational, right? This is a cycle spinning around in a circle.
Can you do that thing again where it's like a little?
Uh-huh. So very important to note that what we're talking about for now would be one cycle, right? One cycle is this going up and down once, right? And then it's over. And so what happens is that this part of the spring goes up and down, which causes this part of the spring to go up and down, which causes this part of the spring to go up and down, which causes this part of the spring to go up and
But if it's
down,
very
which
fast,
causes,
it's very
except it
long.
happens much faster than that, which is why this tracks and moves so quickly, right?
But if you did a big,
I just realized it went here.
Yes, it does. Because why does it come back?
because it's
Because
gonna
it's blocked at the other end,
cycle.
it can't keep going.
It can't keep going. That's exactly
It's
right.
blocked from the wall.
And energy cannot be created or destroyed, right? So when it hits the end, the energy actually bounces off the wall and comes back down the spring, which is exactly what happens to my voice, right? When I'm talking, the sound doesn't just travel out of the room and disappear.
But
It hits
echoes
off the
in
walls.
there. Ah,
It
I
comes back in.
understand.
But it could.
Right.
If you're all the way down there, will it be slower?
No, and that's the most
What
important
if you
part.
make it bigger?
Last part, right, is how the system propagates, right, or translates, how the energy moves depends not on any of this, right, not on any of this. The speed of the wave depends on the medium and the characteristics of the medium itself, right? So let me explain. If I pull this down and I let go, I can count the the frequency. 1, 2, 3, 4, so on. If I pull it down way less and I let go, 1, 2, 3, 4. The timing is the same. The wave vibrational energy is the same. The wave speed does not depend on amplitude. Right? And I can do that with the pendulum. Look, if I pull the pendulum back this far and I let go, 1, 2, 3. If I pull the pendulum back this far, 1, 2,
Oh, that's weird. Oh, I get it.
3.
Oh, wait,
You
but
learned
that's
this in the
more
pendulum lab. What affects the speed
The
of a
energy,
vibrational pendulum?
But that one has more energy, but it has farther to go, and the other
So
one
the
has less
wavelength?
energy, but less.
I have a question.
So what affects the pendulum's vibrational rate? The length of the pendulum. So you see that this one is very long, this one is very short. If I swing this one back and forth, 1, 2, 3, right? It's faster. Because the length is different, the period changes.
So are you
The
saying
physical characteristics of the medium determine the speed, not the amplitude, the period, the frequency, or the wavelength.
So how do you define wavelength?
Yes, wavelength will be how far the wave travels during one cycle.
Isn't that kind of like displacement though?
Isn't it
Yes.
like this? Yeah.
The difference, of course, is that the displacement, Audrey, is the vibration of the spring. The wavelength is the movement of the energy. Right? Remember that the spring is not moving this way, right? It's going up and down. So when I measure amplitude, right, looking at this wave that I have right here in my hand, the amplitude is how far I have moved the spring from this center equilibrium position up like this. The wavelength is how far this wave travels that way before the vibration repeats, right, which is a much different thing.
Wait, I thought if there was one cycle, it would travel there and then that.
The cycle is this vibrating up and down. This is why it's a little tricky to keep straight, right? The spring itself is vibrating up and down. And look at the spring itself right where my hand is. It goes down, and it goes up, 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 right? That vibration up and down is entirely different than the movement going that way.
Sir, if the string, not the string, the spring was like shorter, would it be faster?
Very good. So if I change the length of the spring, or I change the tension, I can change the wave speed. So if I change the medium itself, I can change the speed. But if I just make a taller wave, it works the same, right?
What is the medium?
The medium is the thing that is vibrating.
What if you put more like
Right.
tension on the string? Like what if it?
Right, so if I take this and I pull on this like this, right, then there is more tension in this part of the spring. The wave travels a lot faster. Right, it's hard to see because it already moves pretty fast.
So tension and length.
Right, the physical characteristics of the medium as opposed to any of those.
So it doesn't matter how far
of
you
the
are,
wave
it just
depends on the
happens.
medium.
Exactly.
Wait,
Right.
median?
Medium,
The medium,
Medium.
yeah.
also known as matter, the matter that the wave is traveling
So
through.
the speed of the wave depends on the medium.
Right. And this becomes very important when we think about sound. What does sound travel through typically?
The air.
Air. Generally,
What?
the sound that you hear travels through air. However, if you are underwater in a pool, the sound travels to you differently because it's traveling through water.
That's why we sound weird underwater.
You sound weird underwater because your voice is not made to be underwater like a dolphin's is,
Oh, right.
because you were raised in the air.
Oh,
right?
of course. If I was raised in
But
the
this is
water-
really important because if you think about Richmond is a good train city, right? If you go down to the train tracks and you put your ear on the track, you can hear the train coming before you'll ever see it because the sound travels faster through the steel tracks than it does through the air.
So I've heard they'll actually sit on the road and do
How
that.
far away could the train be?
5 miles
5 miles.
if you listen to the track. But if you're just listening in the air, the sound doesn't travel near as fast or as far,
But
and so
it's
it's
not
much
like
closer.
you'd listen to the track and hear like a choo-choo.
You would hear the vibration. You'd hear the vibration, the rumble of the actual thing.
And the closer it gets, obviously, the louder it gets.
Yes, and we're going to talk about that too. Okay. That's all for today. Does anybody have any questions?